I'm Michael Rendall. I'm a stress engineer at CFMS. A lot of the work I do revolves around trying to automate and optimize structural stress analyses and structures and all the kind of unpleasant things that come with that as well. Also with me, I've got Leo Nolan, systems engineer, who focuses more on the multiphysics models. So we'll hopefully be able to help any questions with that aspect of things. Today, I'll be going through the kind of main issues that come up with uncertainty, looking at more kind of atomic level on specific single models. So what's some of the issues that we come across? How do we normally go about doing them? And what's some of the open questions that we'd like to kind of discuss and see if people have made progress on? To show this, we'll be going through multiphysics models, because that's something we have a bit of a more speciality in at CFMS and has quite a few good analogs to stuff we've been talking about today, these kind of very tightly coupled systems with a high number of dimensions and so on. So just since a lot of you might not be familiar with the stuff we do, I'll give some quick context into the kind of work we do. A large amount of the work we do focuses around trying to model very specific, unique phenomena and systems. So we usually achieve this through a few main kind of methods. The first being multiphysics modeling, which is the main focus of this talk really. A few examples of that we've got is at the top, you can see a simulation we did modeling, I think it was X-rays, using ray tracing and some NVIDIA tool packages. Modeling X-rays going through any kind of arbitrary geometry with certain material properties. And then on the lower GIF, we have a picture of, I think it's the compression molding of composite parts. So you can see you've got this composite filled resin kind of moving around these objects to fill the part, which then kind of move around these arbitrary obstacles and create these join lines and so on. So very tightly coupled and unique modeling challenge there. We also do systems modeling, which sometimes acts as a very important kind of precursor to these, looking at systems in their more fundamental components, regardless of geometries. And then automation and optimization, which has a lot of very tight ties into this, being able to launch analyses without necessarily having a single person making each unique analysis. Uncertainties are prevalent in all of these types of models and need to be very carefully considered when you're doing them. And these uncertainties can come from a few kind of usual suspects. One being numerical uncertainties, which a lot of people will be familiar with. This comes from things such as your mesh sizing or time step sizing. And these are usually a bit easier to quantify because you can usually do some kind of convergence study where you reduce one and see that your result is converging. You know, there's debate if it's correct as opposed to just converging to a single result, but these are usually quite easy to quantify. But the two main kind of sources of uncertainty for us that we usually run to is to do with the characterization of your inputs to your model and comparing your model to validation data as well. So I'll try and focus on these and give some examples of projects we've done in the past. So characterization of inputs. A really difficult source of uncertainty from models comes from the process and model parameters themselves. So a really good example we have of this is some work we've done in modeling resin flow moving through composite parts during manufacture. So this is a very tightly coupled system, which is analogous to a lot of the ones we were talking about before, different systems all very tightly connected. So in this case, we've got resin flowing through a part, which I think the viscosity of it depends on the temperature of it, which also depends on the level of cure, which also depends on the saturation. So all very tightly connected intercoupled system. And here, very small changes in your initial process parameters. So I think plus or minus 5 Kelvin on your initial temperature can have huge effects on the overall behavior of your model. So that's in that example on the side. We've shown that this very small discrepancy in initial temperature creates a totally different behavior in the model. So in one, the tightly coupled nature between the two parameters means the resin freezes up basically at the start, whereas in the other one, with this very slight variation in your input parameters, means you basically get full penetration of resin through the whole part. And this uncertainty is also prevalent in any of the empirical parameters you use to create your models in the first place, which kind of further exacerbates the problem. Additionally, these systems, as I was mentioning, are very tightly coupled. So your usual kind of one of a time sensitivity analysis methods aren't really applicable in this case. You need to look at some more advanced ways of trying to find out what your key drivers of uncertainty are in your analysis. So how do we quantify the input uncertainty? A way we usually do this is to calculate the Sobol indices of the system. So for those of you that aren't familiar, the Sobol indices essentially let you know it's a quantifiable way to show how much uncertainty or variation in your desired output there is given on your input parameters. So the first order ones let you know how much a single parameter has on your desired output, and second order solvable indices allow you to see the kind of interplay between those parameters. And this is usually something that we directly run to see, okay, if there is discrepancy in temperature, how much of an effect will this have on our actual results in the end? But getting these is a whole new problem in itself a lot of the time. So if a model has a very fast runtime, exceedingly fast, like instantaneous, you can sometimes directly estimate the solvable indices using kind of Monte Carlo integration. But you need a lot of samples to be doing this. I think somewhere in the region of, I think it's like 50K samples per dimension we've sometimes seen, which very few applications can actually do this for unless it's a systems type model. So a lot of the time you need to do some kind of surrogate modeling to can increase your number of samples you can get across the space. So there's a few methods you can do if you have some kind of if you have a very low number of samples. There's methods such as RBD-fast to estimate your solvable indices, but usually we'll end up trying to still calculate them directly using some kind of surrogate. But in this, there's a lot more problems which come from this. So in these problems of uncertainty you have where you've got multiple parameters that can be changing, sometimes even just getting a surrogate to fit to multiple dimensions with as many points as you can potentially generate is difficult within itself. And then the uncertainty that surrogate then brings in is also another layer on top of this. A good example of work we've done in a similar kind of field for this type of problem was work we did on detecting corrosion in pipes using ultrasonic inspection. So the aim of this was essentially to see the kind of best, look at the parameters that you can change to get the optimum maximum efficacy in your results. And the key bit to take away from this was, as I was mentioning before, this is a model with very high number of results we had run. So we ran about 20,000 models, producing about 400,000 results across 7 dimensions. So 7 dimensions still, relatively few for what you could do in some of these problems. But a lot of the time, if you're trying to fit any kind of surrogate to this, many of the methods for fitting these involve a kind of number of points by number of point matrix, which in this case would have been about 1.2 terabytes of RAM to store, which is obviously not feasible for any computer, basically. And in addition to this, a lot of your local interpolation methods, so when you're trying to actually evaluate the function, can struggle with this number of points. This is due to things in such Delaney triangulation can struggle with this, which is used a lot in these types of surrogate models. But something we found to be very effective is the use of KD trees, which are very fast to compute and can be queried off based on the nearest neighbors. So they fit a lot better these kind of high number of dimension problems, which we see a lot in single models where we've got lots of sources of uncertainty. Another kind of quick point I want to go over as well is the validating against experimental data. Uncertainty also arises when we're trying to compare against experimental data. And this is because a lot of the time you can be comparing your model to, say, just a single point of analysis. So a lot of times you'll look at experimental data, there'll be no stated uncertainties or no kind of uncertainty bars within this. So it resorts to being these kind of point-to-point comparisons, which ideally isn't great because you can see in this example here, we had this one we showed in the DAWS thing before, where you have 3 different sources that you're trying to validate against, all giving slightly different results. So in reality, it should be some kind of comparison of envelopes of performance as opposed to point-to-point results. But when you don't have this on the experimental end, it's very hard to quantify this, given that the uncertainties in the experimental data can also be very different from your model you're running itself. So quantifying this is very difficult if you can only generate the envelope on one side of the equation. So what's the biggest kind of issues looking forward and things that we'd like to try and solve moving forward? We want to move away from this, as I mentioned before, single point modeling and move towards envelopes of performance. So rather than trying to find a combination of parameters that say give you the least drag in a specific position, F1 cars are a good example for this. If you want to design a car that gives you the lowest drag, and then if you do your traditional approaches where you look at deterministic results, you might get a result, but that only works if everything is to like a degree of temperature and wind alignment and so on. So we want to begin to move away from these type of results and move towards envelopes of performance, which one gives us the best result most of the time, given the uncertainties in the system that we expect to see. To do this traditionally, and the way we've been doing it so far, involves running a lot of models. So in that previous one, I said about 20,000 evaluations, which puts a lot of your more traditional solvers, such as Nastran, in quite a difficult spot, because as you said, it's very expensive to run these things. And then even on that, they're normally core limited since they're designed for these desktop computers. So you need to develop some new tools, whether that be some systems modeling or using other solvers, which we've dabbled in the use of a Moose solver, which is open source, to try and solve some of these problems. So looking forward, other than doing that, something we'd be very interested in the future is trying to see if it's even possible to try and quantify your uncertainty as part of your evaluation of that initial function, rather than having to always resort to running over the whole design space. But this is obviously a very open question, and you know, if it's possible or not depends. But yeah, that pretty much covers it though. If anyone has any questions, feel free to ask.
Just a quick question for clarification about the last point. How do you see the role of CFMS there? You're hoping that you get such solvers which have some inherent uncertainty estimation available, or do you think you will derive something around them? So is it intrusive, non-intrusive? So what's the expectation you have on this point? Wait.
Yeah, I'm not sure. It would be something we'd be looking to see in more solvers, because it's a bit of a hard to even make tangible problem at the start. But it would be better if this was inherent in the solvers as opposed to a CFMS specific thing. But yeah, as you said, not even sure if it's possible in the first place, but it would make sense if we could do some kind of more generalized scheme. But yeah.
Maybe a quick question from myself. Have you experienced any significant model forming uncertainty? Because you mentioned validation in your slide. So how would you deal with model forming uncertainty in general?
What would be examples of that?
As you validate your model, that is unlikely to match perfectly with your data. So how do you treat then that discrepancy that might appear between data and the model?
I think we've done in the past trying to, as I was saying before, running over your envelope and seeing is the envelope that we expect from the model aligning to at least part of it. We don't have this kind of matching envelope from the experimental data a lot of the time, but I think it's trying to see is, okay, given the uncertainties within our model, is there some kind of crossover in this that suggests that the uncertainties may be from the model as opposed to the experimental results? But again, it's very much an open question. That's our current approach, I'd say.
Kind of in passing that experimental data can have errors and it can have uncertainties. Don't you send it back and say, I need to know the error bars and the uncertainty bars?
Yeah.
And otherwise, you're a bit hostage to fortune there, aren't you?
Yeah, that's very important for us. I think it's sometimes trying to, that information does get lost in propagation a lot of the time, and it is, it's a critical point of failure for all this stuff, because if you don't know that, you might be trying to fit your models to incorrect data to start off with, but sometimes there's only so much you can do. You have, especially with these niche models we work with a lot, it's very one-off analyses you'll get as comparison, so it's quite a difficult point to work with. Yeah.
This is so important in this area, I think, this topic, because sometimes the experimentalists think they churn out the truth. No. Yeah. And they don't. No.
That's true. In fact, there needs to be a shift towards acknowledging that it's like there needs to be a range of uncertainty, not just from the modeling side, but from both ends of it.
When you're saying you do handle the length data?
Definitely, a lot of the time it's you just work with what you have at the time.
So there's no way to like close the uncertainty.
No, we've not found a proper way of doing that yet, because you could essentially, I guess, mask your expected uncertainties based on your model onto that, but there's definitely an odd caveat to that you might be just kind of imposing uncertainties that aren't really, because the uncertainties from, say, in that example there of the temperature, the uncertainties from their change in temperature might be far different from what we're expecting in the model. So to superimpose that onto their data is, I think we're just adding more uncertainty in a bad way, comforting ourselves with that.
Well, it's clearly wrong, but what you know is wrong is it's error-free. That's certainly wrong.
Yeah.
So this, if you can get estimates of your errors in your test data, or you can work them out by sensor uncertainty or whatever else, this is where techniques like Bayesian calibration come in. So this is accepting the fact that you have uncertainty in your inputs. You do your most likely calibration. So you're calibrating your models from a probabilistic sense rather than a deterministic sense. We started looking into those. Philip's been one of the ones helping us with that. Not easy, but again, it can add value, or at least recognizing that testing itself is not truth, which is important bit.
The real problem starts if both sides are uncertain and don't really know about it. So you know, both sides are not right. So we lately did something with cryogenic pressure sensitive pain, which itself is a topic of research. So they give you results that they tell you that's the best we can do. It's definitely not the truth, but we can't tell you the truth, and no one else can. And then you got a numerical model where you also know, okay, this is the best we can do. They're not matching, you know, both are wrong. What are you going to do now? Then you're pretty much stuck, lost. I don't know. We tried some Bayesian things, but in the end, if you calibrate garbage against garbage, I don't know. That's something where we are stuck to a certain point, especially if both technologies advance. I mean, it's not only experimentals do their thing and they always do the same thing. They also advance, and at some point they reach a point where they say, okay, this is the best I can do, but it's not that it's like error free, and I can't give you a precise error estimate.